All right, let's talk about innovation. You know, that spark, that aha moment that can change everything. But where does it really come from? Is it just some random flash of genius that strikes like lightning? Or is it a skill, a system that maybe, just maybe, any of us can actually learn? That's what we're going to dig into.
You know the picture we all have in our heads, right? The lone genius scribbling away who suddenly has a eureka moment. We love that story. But what if that whole idea is actually holding us back from making real, consistent breakthroughs? Let's start by tearing down that myth. So, let me ask you this, straight up. Do you think invention is just some kind of magic you have to wait for? Or could it actually be a process, a method, a tool that anyone can pick up and use to solve really tough problems? I mean, think about it. In pretty much any field, engineering, design, you name it, the really difficult problems always seem to trap you in some kind of frustrating trade-off. You make one thing better, and boom, something else gets worse. This idea is so important it has a name. It's called an engineering contradiction. And here's the classic example, an airplane wing. Of course you want to make it stronger, right? So you add more material. But what happens? Well, it gets heavier. So you've improved the strength, but you've made the weight worse. That's a contradiction. Now, the easy way out is a compromise. Make it a little stronger and a little heavier. But what if you didn't have to compromise at all?
So here's what we've got on top. First, we're going to introduce a system designed to solve exactly these kinds of problems. It's called TRIZ. Then we'll dive deep into 5 really cool principles that use natural forces and material properties. And finally, we'll see how this all fits into a complete toolkit for invention.
Okay, so if we're not just going to sit around and wait for that eureka moment, what's the alternative? Well, it's a structured system, and it was designed specifically to smash through those so-called impossible compromises. It's called TRIZ, which is actually a Russian acronym for the theory of inventive problem solving. It was developed by a Soviet engineer named Genrikh Altshuler, who asked this really radical question. What if invention isn't an art? What if it's a science? He spent his life trying to find a repeatable, reliable way to solve those annoying contradictions without making a trade-off. And this right here, this is the whole philosophy behind TRIZ, boiled down. Altshuler was convinced that no matter how unique or complex a problem seemed, it was probably just a version of a problem that had already been solved before. If problems repeat, he thought, then the solutions must repeat too. So how in the world did he find these patterns? Well, get this. He and his team undertook this massive, almost unbelievable task. They analyzed over 2 million patents from all over the world. They didn't care if it was for a tractor or a spaceship. They just looked for the core inventive idea, the clever trick that made it work. And what they found was just incredible. Turns out, the same fundamental solutions kept popping up over and over and over again. They managed to distill all of that human ingenuity down into just 40 inventive principles, a universal toolkit for problem solving. And today, we're going to check out the last 5. All right, let's crack open this toolkit, shall we? We're going to start with 3 principles that are almost beautifully simple because they use the fundamental forces of nature that are literally all around us. First on the list is Principle 36, phase transitions. Now, this is all about using the really powerful effects that happen when something changes its physical state, like water freezing into ice or boiling into steam. The core idea here is to take advantage of things like volume change or heat absorption when a substance goes from, say, a liquid to a solid. There's this awesome story, maybe a legend, but it perfectly illustrates this, about Hannibal crossing the Alps. The path was blocked by these huge boulders. So as men would pour water into the cracks in the rock, and overnight the water would freeze. As it turned to ice, it expanded with incredible force, literally splitting the boulders apart. That's using a phase transition as a tool. Next up, we have Principle 37, thermal expansion. Now, this is something you've probably seen a million times without even thinking about it as an inventive tool. It's based on a simple fact of physics. Most stuff gets bigger when it's hot and shrinks when it's cold. So how is that a tool? Well, picture this. You've got this metal shaft and you need to get it into a bearing, and the fit is super tight. You could just try to hammer it in, but you'd probably break something. Instead, you could use this principle. You heat up the outer bearing just a little so it expands. Then you cool down the inner shaft, maybe with liquid nitrogen, so it contracts. They slide together perfectly. And when they both get back to room temperature, you've got an unbelievably strong, perfect fit. No hammering needed. And the last principle in this little group, number 38, is all about chemistry.
It's called using strong oxidants, and it's basically about hitting the accelerator on a chemical reaction.
So sometimes the plain old air around us just isn't reactive enough. This principle says, hey, why not give it a boost? You can enrich the air with more oxygen or go all in and use pure oxygen. Think about it. A regular torch that just uses fuel and air, yeah, it's hot. But an oxyacetylene torch, which mixes the fuel with pure oxygen, that thing is on a whole other level. It gets so much hotter that it can slice right through thick steel.
All right, so we've seen how to use the forces of nature. Now, let's switch gears and talk about the actual materials we're working with, starting with the next couple of principles. Okay, so this next one, Principle 39, is basically the polar opposite of what we just talked about. Instead of making an environment more reactive, this one is all about making it completely, well, inert, non-reactive. Sometimes the air itself is the enemy. The oxygen and the moisture in it cause rust, decay, all sorts of problems. So the solution is simple. Get rid of the air. You replace it with an inert gas like argon or nitrogen, something that just doesn't react with anything. This is exactly how they preserve priceless things like the original Declaration of Independence. It's not just behind glass, it's sealed in a special case filled with argon gas to stop the air from slowly destroying it over time.
And that brings us to our final principle for today, number 40, composite materials. And honestly, this one has completely changed the game in modern engineering. It's all about getting away from the idea that you have to use just one single material to build something.
The whole idea with composites is to combine different materials so you get the best properties of each one without the downsides. Let's use a surfboard to see what this looks like in the real world. A traditional wood surfboard, it works, but it's heavy and you're limited in the shapes you can make. But a modern fiberglass board, which is a composite of glass fibers for strength and a plastic resin to hold it all together, is way lighter, much stronger, and you can mold it into these super efficient complex shapes. You solve the contradiction. You get strong and light. So that was a whirlwind tour of 5 really powerful principles, right? Let's zoom back out for a second and look at the big picture. And it's so important to remember, those 5 principles we just covered, that's just a tiny peek into the full TRIZ system. There are 40 of them in total, 40 different, proven, repeatable strategies for solving tough problems, all of them discovered by studying the world's most successful inventions. And that is the core idea I want you to walk away with today. Invention doesn't have to be some mysterious, unpredictable art form. TRIZ shows us that it can be a system. It's a way of looking at our hardest problems as contradictions, like wanting a wing to be strong and light. And then it gives us a roadmap to find a truly inventive solution that does both, with no compromise. So, I'm going to leave you with a question. Now that you know this secret, that innovation is a method you can learn, not just some random magic, what's the first contradiction you're going to tackle? What's that impossible problem that you're going to solve first?